Hello, my name is Alex Caston and I lead the non-invasive bioelectronics group at the University of Manchester. In this presentation I'm going to go over some of our work on edge machine learning, that is implementing artificial intelligence in a smartphone in this particular case. I'll start off by giving some of the background from my lab and the motivation for doing edge machine learning in a smartphone, and then some of our previous work on that topic which the current paper really builds upon. And then we'll take a look at the LSTM deep learning network that we've implemented here and how well it performs when we run it on a smartphone. Broadly, my lab is interested in wearable devices, in all of the different aspects of how do we get data from you up into the cloud. And in particular, we're in electronic engineering, so we're interested in some of the red boxes on this slide, the kind of hardware and software that go into the device itself. Of course, in some ways, wearables are a mature, commercially available technology. In other ways, there are lots of opportunities for making them better, for making them more accurate, for making them have lower power consumption, so they need less charging, and also for better integrating them into the care system, making sure that the data is of real use and that they're measuring the modalities that users and clinicians really want to be measured. And so that is what my lab focuses on. Today we've got activity across the entire spectrum of interfacing between biology and electronics, looking at the physical interface, looking at the instrumentation, looking at the signal processing and machine learning, and then how we start to close the loop and make complete sense and actuate devices. In this work, we're particularly interested in online machine learning, so implementing online processing of the wearable data that we get. When we implement our machine learning, either kind of in the wearable device itself or in a companion smartphone device, that's known as edge machine learning. And there's a number of benefits for doing that. Traditionally, it was to decrease power consumption, because wireless transmission of data consumes a lot of power. And if you can run your processing locally, you don't need to transmit the raw data to a data center for processing. You can just transmit the end result of any analysis, and that would save a lot of power. Today, we're really interested in it for privacy preservation, for keeping data local to the person. So we're collecting signals from the user and we're analysing them, and the key results of that data will be passed up the chain to the cloud and similar, but the raw data never leaves the physical locale of the user. And then we're also interested in it for closed loop systems. If we want to have sense actuate systems that respond to the data that's being collected and do that in a very timely manner, we often don't have time to send data to a cloud, to a data center. A round trip time can easily be a couple of 100 milliseconds, and for very responsive systems that's going to be too much. And so both of those really motivate a processing of our data in the edge device that's near to the person. By processing, I mean machine learning, artificial intelligence, and in particular deep learning today. There's a huge amount of literature that is emerging about the use of machine learning, and that's the sort of data processing that we want to enable in our edge device. In my lab, we're particularly interested in human activity recognition. So this means using wearable devices principally accelerometers and gyroscopes, in order to infer what the person is doing. And we've published a number of papers about human activity recognition in recent years. And at the moment, these are largely based upon the offline processing of data. So we've collected our data, we've transferred it to a computer and done the analysis there. Now we want to look at how can we do the analysis in real time in a companion smartphone to the data collection device itself. For doing that, we've actually been working on this topic for a little while. So we had a paper in IEEE Access in 2019, which looked at implementing both CNN, so cellular neural networks, and LSTMs, long short-term memory networks, on a smartphone device. And we did that using the TensorFlow framework. And that worked very well. We got a performance of about 92%, which is very much in line with the performance for human activity recognition from other papers. We were able to optimize the network using different number representations for the weights in order to reduce the memory footprint quite substantially, and then run that using a power consumption of about 40 milliwatts. And so we were very happy with that. But, of course, today, in addition to TensorFlow, the library, we also have access to TensorFlow Lite. Now, this is a version of TensorFlow designed for implementing deep learning models, specifically on edge devices, like wearables, like smartphones. And so we should be able to use that to get much better performance. The challenge in that was that until fairly recently, LSTM networks haven't been supported in TensorFlow Lite. And so our aim in this work was to take our LSTM networks, port them to TensorFlow Lite, run them on a mobile phone to see the kind of performance that we can now get with the current machine learning state of the art. So the process for doing that is shown on the screen here. We start off with what's called an offline prototype. So we do our deep machine learning on a computer, on a desktop, whatever, in exactly the same way as we always would. And then when we got that prototype, we convert it to a TensorFlow Lite representation of the same network. And then we look at optimizing that network, looking at how can we change the weight functions so that we can reduce the memory footprint and so on. And so in this work, we made a network for human activity recognition using accelerometer data and gyroscope data as the input. And that's just a public data set coming from UCI. And it's got labels for 6 activities, things like walking, standing, going upstairs, going downstairs, and so on. So we've got the structure of our network on the screen here with 2 LSTM layers, and we did some investigation into the optimal number of layers, the optimal number of LSTM units per layer, in order to decide on the final structure for us to use, with that being the structure that's in the middle picture here. And then we ported that TensorFlow network to TensorFlow Lite and put an app wrapper around it, and you can see a screenshot from that on the left here. And so that version is operating in real time in the smartphone emulator in Android Studio in this case. It outputs the probability of being in each of the different activity states at any point in time. And the performance is about 92%, nearly 93%. So very much in line with the previous state of the art for offline networks. And then we looked at the optimization of that, so changing the number representations within the network. And what we could find was that for a very minimal reduction in performance, we could get very substantial reductions in the memory footprint, down to the kind of tens of kilobytes sort of level. And we're operating on a phone here, but that's putting us within touching distance of being able to implement some of these networks in wearable class hardware within the portable device itself, not relying on a companion phone. And that's all I wanted to go over in this presentation. We're building on our 2019 work where we were able to use TensorFlow to implement CNN and LSTM networks on smartphone class hardware. Now we've got LSTM support in TensorFlow Lite, and so we've been able to implement LSTM networks in TensorFlow Lite and run those on smartphone class hardware. And the next step in our future work will be to deploy those same networks but into the hardware of a wearable device itself.